Today we're going to learn a new technique for finding antiderivatives called antidifferentiation by parts. This is one of the things that your friends who are taking AB do not have to learn. This is a BC only topic. And it allows us to take antiderivatives of things that we would have no chance of doing it without. So what it's based on is it's based on the product rule kind of in reverse. Let me explain. So if we take the derivative with respect to x of, we're assuming u and v are both differentiable functions of x. If they're not, this whole thing goes to hell in a handbasket, okay? Remember, that's u times dv dx plus v times du dx, right? Not a problem. All right. Rearranging this then, I'm subtracting the v du dx on this side and then switching sides. So we get this expression. If we then take the integral of each part, so over here, if you think about the dx's as if they were numbers and we could cancel them, they're not, but this works almost all the time. This is part of the genius of using differentials for these things. You get the integral of u times dv is equal to, here we have the derivative of u times v, and then we're taking the integral of that. Well, that gets us back to u times v. And here again, imagining that those dx's cancel, we have minus the integral of v du. This is the integration by parts formula. The integral of u dv is equal to uv minus the integral of v du. It is something that you absolutely need to memorize because it's not something you're going to be able to go, oh, I know that came from the product rule. It's unlikely you would be able to, under a pressure situation like the AP exam, be able to come up with that. So this will allow us to do integrals like this one, where it's the product, not the sum or difference of two totally unrelated functions, or totally different kinds of functions. I shouldn't say they're unrelated. They are. They both have an x in them, but completely different kinds of functions. So what we would do on this is we're going to let u be equal to x. And we're going to let dv be everything else that's in there. That's in the integral. So that'll be cosine of x dx. Then du, well, the derivative of x is just 1, so du will be equal to dx. And then on this side, we have the derivative. We have dv, but we want to know what is v equal to. So what is the antiderivative of cosine of x dx? Sine of x. And we don't have to worry about the constant when we do that. Occasionally students go, shouldn't we have a plus c? Yeah, it turns out it doesn't matter. So now, using the formula, we take u times v, so that's x times sine of x, minus the integral of v times du, which is sine of x dx. So then we have x sine of x. The antiderivative of sine of x is negative cosine of x, but since we have this negative here, this will be plus cosine of x plus a constant. Okay? And hang on just a second. I feel like there's something wrong with that, but I don't know what it is. I'll come back to it. And we can do this with all kinds of functions. Now, the question always becomes, well, what are we going to let be u and what are we going to let be dv? And I'm not big on things like this. I think you guys have been around me long enough to know that I'm not big on little cutesy things to help you remember. This one I think is worth it. The acronym LIPIT, where L is for logarithm, I is for inverse, P is for polynomial, E is for exponential, and T is for trig. This is the order in which you should decide what u is. So if you don't have a log, you look for an inverse. If you don't have an inverse, you look for a polynomial. If you don't have a polynomial, you look for an exponential. If you don't have an exponential, you look for trig. If you don't have any of those, you've done something wrong. Okay? Whichever one of those you come to first, that's going to be your u. So, for example, here, we want to solve dy dx is equal to x natural log of x subject to y equals -1 and x equals 1. All right, so we know that y is going to be the integral of x natural log of x dx. Notice we have two completely different types of functions being multiplied together. That's always the clue that you're going to be doing integration by parts. We apply our acronym LIPIT. There's a logarithm, so I'm going to let u be equal to the natural log of x. And dv is always everything else that's in the integrand. That is, in this case, x dx. So then du, the derivative of natural log of x, is 1 over x dx, and v will be the antiderivative of x dx, which is well, this wasn't supposed to be a hard one.
1/2 x squared?
Yeah, 1/2 x squared. So we're going to have u times v. So I'm going to have -1/2 x squared natural log of x. You can write it in the other order, but I tend to write the logarithm last so there's no confusion as to what the argument on the logarithm is. Minus the integral of v du, and this is where the genius part comes in. You're like, oh, cool. When I multiply u and dv together, I get just 1/2 x dx. So now I have something that I can deal with. This is going to be -1/2 x squared natural log of x minus the antiderivative of x. We already did that. That was 1/2 x squared, so this is going to be 1/4 of x squared, all plus c. In almost every problem, when you get to this taking the antiderivative stage, it's going to be the same antiderivative you were doing over here. Almost always. All right, let's try another one. So here we've got x squared e to the x. So logarithm, no. Inverse, no. Polynomial, yes. So we'll let u be equal to x squared. And dv be everything else that's after the integral sign, e to the x dx. du then is 2x dx. And v is the antiderivative of e to the x, which is e to the x. So we apply the rule u times v, so that's x squared e to the x, minus the integral of v times du. So that's 2x e to the x dx. Now, you're like, I still have two unrelated functions, right? Or different types of functions. But this is of a lower degree than it was. And if I do it again, it'll be of even lower degree, meaning it'll be a constant. So that'll be nice. You can, if you want to, remember later on in the problem to distribute the negative sign through everything else that you get. I try to minimize mistakes with signs because I make them all the time. So what I actually do is at this point I go, okay, I'm going to have to do this again. I'm going to make this plus a negative 2x e to the x. And when I designate my u, I'm going to make it negative 2x. So I don't have to worry about distributing later. Again, you can if you wish. Years ago, I was like, I'm going to stop doing that. And then dv is e to the x dx again. So du is negative 2 dx. And v is the antiderivative of e to the x, which is e to the x. Don't forget to keep the first term that you had, x squared e to the x, plus u times v, that'll be negative 2x e to the x, minus the integral of v du, so that'll be minus the integral of negative 2 e to the x dx. Nice thing about that is those both cancel out so that it's positive. So I've got x squared e to the x minus 2x e to the x plus 2 e to the x dx. Now, I want you to notice on this, no dx, stupid, plus c, not dx. I want you to notice that we started with the polynomial x squared, and look what we've got here, x squared, 2x, 2. Those are just the derivatives, right? So what you can do is you can do what's called tabular form for a problem like this. Since you only had to do integration by parts twice, you certainly don't need to. But what you can do is make a column of u and its derivatives and dv and its antiderivatives. So we let u be equal to x squared, so the derivative is 2x. The derivative of that is 2. Derivative of that is 0. Always go all the way down to 0. We only do this when we have a polynomial times something else. It's not going to work out very well if you have something else. And then e to the x, whose antiderivative is always e to the x. And we multiply down a level. X squared times e to the x, and you're like, wait a minute, it's supposed to be minus on this next one. Yep, we have to go plus, minus, plus, because of the negative sign in our formula. And the reason that the third one is positive is because we would have done your integration by parts again, right? So it's going to be minus, minus, which is plus, and then minus, 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 which is back to minus, et cetera, et cetera, et cetera. And we'd end up with this in a much quicker fashion. If we have time at the end of class, we're going to do one more of those. In the meantime, though, we're going to do something that is ugly. Oh, so ugly. So we've got two completely different types of functions here. You're like, great. All right. So logarithms, no. Inverses, no. Polynomials, no. Exponentials. So that's what we're going to let be u. So u is going to be e to the 2x. dv will be everything else after the integral sign. So that'll be cosine of 3x dx. du will be what?
2 e to the 2.
Yep, dx. And v will be, we're taking the antiderivative of this.
3 sine. 1/3.
Yeah, it's 1/3,
Oh, okay.
right? It's 1/3 sine of 3x. So we've got u times v. So that's 1/3 e to the 2x sine 3x. Minus the integral of v du. So that's going to be 2/3 e to the 2x sine 3x dx. Much like I did in the previous problem, so that I don't have to worry about distributing the negative later, I'm going to go ahead and make that plus and make this a negative 2/3. Do the same thing. And occasionally, students are like, oh, it didn't work out the first time. I should switch which one is u and which one is dv now. Don't. Okay? Stick with what you started with. So u is going to be negative 2/3 e to the 2x, and dv will be sine 3x dx. So then du is going to be negative 4/3 e to the 2x. And v is going to be negative 1/3 cosine of 3x. I left off the dx over there. Sorry about that. So now I have 1/3 e to the 2x sine 3x plus u times v. They're both negative, so this is going to come out to be positive. 2/9 e to the 2x cosine of 3x minus the integral of v times du. So minus the integral of, what is that, 4/9 e to the 2x cosine 3x dx. If you look at that, I think you can see if we do it again, we're not going to get anywhere. It's not going to get any better. You're like, well, have you spent all this time leading us astray on this problem? Actually, no, not this time. Sometimes I'll do that to let you see, yeah, this is not the right way to go. But in this case, it is, because this is equal to the integral of e to the 2x cosine of 3x dx, right? Notice this is 4/9 of that exact same integral. So I'm going to add 4/9 of the integral of e to the 2x cosine of 3x dx to both sides. When I do that, I get all of this stuff that I had here. The worst part about this, honestly, is all the writing you have to do. And when I add these two things together, I've got 1 times the integral plus 4/9 of the integral. So 9/9 of the integral plus 4/9 of the integral is 13/9 of the integral. So I just need to multiply both sides by 9/13. And I will have solved for the integral. So I'm going to multiply this by 9/13. The 3 will go into the 9 3 times, so I'll end up with 3/13 e to the 2x sine 3x. Plus here, the 9's will cancel. I'll have 13, I'll have 2/13 e to the 2x cosine 3x plus c. This is called solving for the unknown integral. It almost always only occurs when you have an exponential and a trig function. And the reason it works is because if you think about it, when you take the derivatives of the antiderivatives of the trig functions, it's circular, right? It comes back to itself. That's the reason why it works. You could actually do this instead of twice. It would be dumb, but you could. You could actually do it 4 times and then do it. Ugh. Don't know why you would want to. All right. Page 3. This is one where you're like, okay, this is different because I don't have 2 different types of functions being multiplied together like I've always had before. But this one actually can be done by parts. You're like, really? Yep. So I'm going to let u be equal to the natural log of x. And I'm going to let dv be everything else that's left, which is just dx. Then du is 1 over x dx. And v, the antiderivative of dx, is x. So using the formula, we've got u times v, so that's going to be x natural log of x, minus the integral of v du, so minus the integral of x times 1 over x, well, that's just 1. Taking that antiderivative, we have x natural log of x minus x plus a constant. In my mind, that's not an integral that comes up so often that you should memorize it. Some people do. Just that the integral of natural log of x is x natural log x minus x plus a constant. If you want to memorize that, great. I don't think it comes up often enough to do it. And most of the time it's not quite that. They have something else mixed in. All right, let's do this one. And you're like, okay, is this the same thing? Yes, it is. We're going to let u be equal to the sine inverse of x. And dv be everything else, which is just dx. Then du is 1 over the square root of 1 minus x squared dx. And v is x. So we have u times v, x times the sine inverse of x, minus the integral of x over the square root of 1 minus x squared dx. And this is part of why the one we were talking about, number 24 on the homework, part of why I put it on there is so that when you look at this, you go, okay, I can't make that an arc sine because it's got this x in the numerator. I'm literally going to do a u substitution on this. This is x times sine inverse of x. I'm going to go ahead and put the negative in here just so I don't have to deal with it later. I'm going to let u be equal to 1 minus x squared. And this is not integration by parts anymore. This is integration by substitution. D would be negative 2x dx. You're like, great, I have a negative x dx, so I'm just going to make 1/2 du equal to negative x dx. So this will be plus 1/2 of the integral of u to the negative 1/2 du. So that's x sine inverse of x plus 1/2 times, I add 1 to the power, so that'll be u to the 1/2 times the reciprocal of the power, which is 2, plus a constant. Those happily cancel each other out. And we get x sine inverse of x plus the square root of 1 minus x squared plus a constant. And you probably don't remember these problems, but because I've been doing it for so long, I recognize that when we were first learning about derivatives of sine inverse, they gave you something like this and said, find the derivative. And we were always surprised at how much things collapsed and canceled together, so you just ended up with this. How did they generate this? By doing exactly what I just did here. All right, let's try another tabular. So since I have a polynomial function, and for tabular what you need is you need a polynomial and you need something that you can, is that really our bell? I guess it is. Wednesdays, short day. 10:50, yep. So you would do x cubed and its derivatives, and e to the x and its antiderivatives. And always one down and alternate signs. So this would be x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus a constant. All right,